kind of through technology and just, well, anyway. And it's all powered by floating point numbers, okay? So anyway, here we go. Week 6. Happy Monday. Welcome back from a weekend of studying. Or whatnot. Okay. So I sent out your time slots for the midterm exam, and I will send out a seating chart probably tomorrow, and so if you're taking it in the morning, it'll be in this classroom, and I just arbitrarily named the rows A, B, C through H or J, and then the seats are 1, 2, 3, whatever. Okay, and so you'll find. So I'll email out this picture of the classroom, and then I'll with the seats labeled, and then you'll get an email with like your seat number is this. Okay, and then if you're taking it in the evening in Kinsey, those seats are already numbered. They already have numbers like 101, whatever. Although like some of the labels have fallen off, but that's what you get. So you'll get you'll get a seating chart for that as well. And we'll see you guys on Wednesday for it. Okay. But floating point numbers. So let's talk about floating point numbers. And so when we're working with numbers on the computer, right? And I type in like 3.5. What's the type of that thing in R? It's type double. Okay. Now, it's easy to think of type double as like real numbers, okay, like the real number line, but it's not the real number line, right? And that's a very, very, very important distinction, okay? So when you think about the set of real numbers, like how do we define the set of real numbers? That's like a whole course, right? I think Math 131A is like, what is real numbers and stuff, and it's very complicated, and I was not a math major. I actually, I studied engineering undergrad, and then I studied statistics, and then when they were talking about all of this theoretic math stuff, I was like, I have no idea what's going on. So it was rough, but anyway, so your real analysis stuff, you can think of this, but kind of simply, just a very, very simple idea of what the real number line is you can think of kind of all of the points on some infinitely long line, okay? And the integers are equally spaced out, and there's infinitely many real values, okay? And you pick any two locations on the real number line, and there's infinitely many values between them, right? So you pick 0 and 1, there's infinitely many values between there. You pick 1/2 and 1, and there's infinitely many values, right? And like how many values are between 1/2 and 1? It's like the exact same number as the values between 0 and 1 and 0 and a billion, okay? And it's like that's hard to imagine, but there are like the exact same number of this, uncountably, I don't know, whatever, Aleph, some level, something on all of these different levels of infinity, right? There's infinitely number integers, but there's infinitely more real numbers. There's just, I don't know, right? There's the same level of infinity for integers as there are rational numbers, but it's anyway, that's beside the point, okay? Anyway, because of the real number line and the properties of real numbers, like we teach you this stuff, associativity, distributive property, commutative property, like you learn this probably in what, 5th grade, 6th grade, 7th grade, something around there, and you learn like, maybe you didn't learn these formal names, but you were taught like, oh, you do 3 times 6, and it's going to be the same thing as 6 times 3, and it doesn't matter what order you put these in, right? And something like that, right? Like 6 divided by 10 is the same thing as 1 divided by 10 times 6, and things like that, and you learn all of this stuff, and this has like, I think at this point this is like deeply ingrained in the way you perceive numbers and stuff, okay? Now, when you deal with computers, however, it's different. All of these rules kind of break down when you're dealing with computers, and it's very jarring when you encounter it, because we're so accustomed to this thing that numbers operate this way. And when you're dealing with numbers on the computer, they look like they're real numbers, but they're not. And these properties break down, okay? And you've already encountered this already, because you get things like you're doing something and you're expecting 0, and you don't get 0, you get 1.58 times 10 to the negative 17. And we're just like, and so far we've just said like, it's close enough to 0, so we'll treat it as 0, and you guys were like, okay, I guess. But if you think about that, like, that's weird, right? That's weird. But that's a side effect of this floating point number business, okay? So one property of real numbers is that every number has a decimal representation, okay? And this is how we formally define what decimal representation is. But basically, like, 1/2 is 0.5 with infinitely many zeros, 0.5000000, right? 1/3 is 0.33333333, and those threes go on to infinity, okay? And you can represent 3/3 or one as 1, and an exact equal representation of the number 1 is 0.9999999 off to infinity, right? And this is a little bit controversial because a lot of people don't like it. But if you do 0.999 and you say those 9s go on to infinity, that is exactly equal to 1. Okay, and that's kind of this side effect of decimal representation. Okay, and so anyway, you see this number 5,413.29 and 29 100ths would be 5 times 10 to the 3rd plus 4 times 10 to the 2, 1 times 10 to the 1, and so on and so forth. And basically you have the numbers times 10 to the something, and it goes 10 to the 3, 10 to the 2, 10 to the 1, 10 to the 0, 10 to the minus 1, 10 to the negative 2. Okay, this is all review, and I think you're accustomed to this. We have scientific notation, and you might have called it scientific notation. You might have had some other kind of name for it, but the key with scientific notation is that your first, the digit in front of the decimal point has to be some number other than 0, okay, 1 through 9, and then you have all of these other digits behind it, and it's going to be multiplied by 10 to some power, right? So you represent 1,000 as 1 times 10 to the 3rd, and 0.0001 0.000123 would be like 1.23 times 10 to the negative 4, I think is what I said out loud. And so anyway, this is how you represent. So this number can, this would be non-normalized scientific representation. This would be weird, but you could, this and these are exactly equivalent. This is kind of your normalized scientific notation where it has to be some number other than 0 in the front. So we have 5.41329 times 10 to the 3rd. And this is useful when representing these, really big or really small numbers. This is what Avogadro's number, the number of things that make a mole. Okay, yeah. You have a question?
Yeah. So I'm reading the slide, and then on slide 6, it says m and n are integers. But how do you like the first expression are equal to me when as m times n? If m and n are both integers, how do you get it to a decimal representation?
Wait, the alternative expression to decimal representation is scientific notation. Oh, I guess, I'm sorry. Yeah, m is not an integer. Sorry, that's okay. Just strike that out. I apologize. Okay.
Is the bottom formula like the one that has a dot
in the A? I think so.
Okay.
Yeah. And it should be each of these things, and A here are integers. Each of those things are integers. Yeah, are digits, I should say. Okay, so humans often represent real numbers and perform arithmetic calculations using decimal representation. And some things have finite decimal representation, like 1/2, okay? But a lot of them require infinite decimals to represent them, such as irrational numbers, and a lot of rational numbers still have infinite decimal representations, okay? And so when you write a decimal representation down on a piece of paper, right, you can't write infinitely many 3s, right? So you either have to do an approximation or you do some kind of mathematical notation, right? Maybe you put a bar over the 3 to kind of indicate that they go on, or you can do ... to indicate that they go on, okay? Now, in the computer, we cannot represent anything with infinitely many values, right? Because if we wanted to keep all infinitely many values of, say, pi, how much memory and how much storage would you need on your computer? You would need to have infinite memory, all right? And that just doesn't exist. Now, we're at this technological marvel where you can buy, what, a terabyte of data and it fits in this little SD card, okay? And that's like mind-blowing, but a terabyte is still not infinity, okay? And it would also be a waste, right? If you said, okay, I have a terabyte of data, okay, what do you have on there? It's just the numbers of pi, and you'd be like, oh, I mean, I guess that's cool. And I mean, like, there's something special about pi, so you're like, oh, that's cool, pi, right? But if it's like, oh, I use this to represent the number 1/3, okay? I used this full terabyte of data to represent the number 1/3 because guess what? The 3s keep going on forever, and I didn't feel right to stop after, 800 trillion of these things. So I kept going, and now I filled up my entire terabyte hard drive. And now I want to represent the number 1/9, and I need to buy another terabyte. And it's just, okay, it's dumb, right? So we say, okay, well, let's just use 64 bits to store our numbers, okay? And you go, 64 bits? I can only store 16 decimal places. Yeah, sorry, that's what we can do, okay? So things are only represented approximately, okay? So computers will store numbers in binary representation, but base 2, but the effects of this approximation can also be seen with finite decimal representation, all right? And so I don't know, did you guys ever, probably, right? So I have this old calculator, okay? And I videotaped myself using this calculator. But if you find like an older calculator, I mean, this is not old, but just like old technology calculator, right? So your modern calculators, like if you have a scientific calculator, it'll probably do these things correctly. But if you play with like an old one, you're going to see something like this, okay? So what's going to happen on the calculator if I do 10 divided by 3? I'm going to get 3.333. And then if I take that number and I multiply by 3, what am I going to get back? Yeah, so you guys can already kind of see what's going to happen, right? So let's go to this video, and I hope this works. Maybe it'll play a commercial. Okay, here we go. All right. So here's 10. I divide by 3. I get 3.333. I'm going to take that number, multiply by 3, and I don't get 10 back. I get 9.999, right? So I think this is, we're kind of expecting this. 10 divided by 3 gives me this. And we multiply by 3, and we get, again, we don't get 10 back. And maybe that's not shocking to you, right? Because we're kind of accustomed to seeing something like this, okay? All right, so we get 9.999. What happens if I do this? 10 times 3, I'll get 30, and then I divide by 3, and get back 10. Okay, now this is almost entirely pointless to do, but I will do it. All right, 10 times 3, we get that. We divide by 3, we get that. Okay, we get 10. Okay, so doing exactly what we expect. Okay, but this is quite profound. If you think about what is happening mathematically, we have broken the rule of associativity, right? 10 divided by 3 times 3 is not equal to, we get 9.9999 is not equal to 10 times 3 divided by 3, okay? And maybe we're accustomed to working with calculators in such a way that this doesn't bother us anymore. But if you think about like how real numbers work, this should bother us. This should say, hey, what is going on, right? So the order in which we do these operations now makes a difference, okay? Same kind of thing. If you do the square root of 2 and then you square it, you're going to not get 2 back. You get 1.99998. And if you do 2 squared and then you take the square root of that, so if you just do like 4 square root, you get 2 on the calculator, okay? And again, this kind of breaks the rules in for real numbers, right? And I have little video clips of these things, but it's probably not worth doing. And before I forget, let me give you your first view quiz answer. Today's first view quiz answer is the letter D. D as in dog. D as in dog is your first view quiz answer. All right, so you can try this out if you have R right now. Say 0.1, store it as A, all right? And you say print A and you get 0.1, all right? And then for B, do 0.3 divided by 3. Okay, and you say print B, and you get 0.1, all right? And then you say, is A equal to B? Is A equal to B? You do A equals B, and at face value, we would expect A equal B to be true. But then if you try it on the computer, what do you get? You get false. You get false, okay? And this is basically, you know, what happened on the calculator when I did 10 divided by 3 times 3 versus 10 times 3 divided by 3. We're expecting those things to be equal, but on the calculator, it's not the same. And on the computer, this thing, 0.1 versus 0.3 divided by 3, these are not identical. They're not exactly equal to each other. And we get a false here. Okay. Similarly, I could say A is 0.1 plus 0.2, and on face value, it looks like 0.3. I can say B is 0.3, and at face value, it looks like 0.3. And if I do, is A equal to B? And again, it looks like we have 0.3 and it looks like we have 0.3, but internally, are these two things equal? And they're not, okay? And I don't know if this is jarring to you or if this is just kind of like, oh, okay. But yeah, I mean, I'll demonstrate right here. If R will start up for me. Okay, so if I do A is 0.1 plus 0.2, okay? So A, it looks like 0.3, it sure looks like it, all right? And if I say B is 0.3, okay? But if I say is A equal to B, it's not, right? A is that, B is that, right? So if you're like doing some coding, like this would be very frustrating if you're expecting these two things to be equal to each other, but it keeps saying A equal B false, right? So, and this is just something that's inherent, not just to R, but to all computers, okay? All computers where we only have finite representation of numbers, this is going to be something inherent to that process where you're going to get stuff like this and they're not equal to each other. Question? Okay, yeah. So it's not just R, it's all computers, yeah. Yeah. So if I have D is 0.3, okay? So D is 0.3 and, you know, B is 0.3, right? So D equal to B, that's true. D is this and B is this, right? But then, but here's the thing. It's like, now you have to keep track in your head, like, how did I arrive at 0.3, right? Did, you know, and you ask, what's D, what's B, what's A? And they all look like 0.3, but you say, is A equal to D? And that's no, but B equal to D, that's true, right? This is this is just frustrating. Now it's like in your head, you have to keep track of like, oh, I found A by doing 0.1 plus 0.2, and then, you know, maybe E, I'm going to do 10 divided by, or what am I going to do? 3 divided by 10. All right, so here's E. And like, is A equal to E? That's not true. Is D equal to E? That's true. You know, like which of these things equal to each other? And you know, it's going to be rough. Okay. So here's just a sequence, right? So here, you know, if I say make a sequence from 0 to 1, increment by 0.1s, right? And if I say, okay, take this 0.3, and that's 0.3, and here's B is 0.3, and I say, are these two things equal to each other? It's like now we're like just playing some guessing game. It's like, maybe they're equal, maybe they're not. Okay, so they happen not to be equal. Okay, and just more of this stuff, right? So again, in real numbers, these two things are exactly equal. 4/5 times 3 times 5/4. And here I got 4/5 times 3 times 5/4, right? I just grouped these things together, and they look like it's the number 3, but again, these things aren't equal to each other, right? And now you're just like, well, nothing's going to be equal to each other, but it's not true. Like, things do end up being equal to each other. And so you can kind of try to see what's going on, and you can say options digits equals 20. Okay, or you know, when you print out a number, you can do print x comma digits equals 20, and that will keep a whole bunch of decimal places, and we can kind of get a sense of what's happening. 0.1 internally is not actually 0.1 with infinitely many zeros. It's represented with 0.1000001, and here I got 0.20001, and 0.1 and 0.2 added together gives me this, whereas 0.3 is stored as this, and so these two things aren't equal to each other. Okay, so these kinds of things, this is what's happening internally. Okay, and so here, and then here's just another thing. I've got 0.3, 0.4 minus 1, 0.5 minus 2, 0.6 minus 3, and 0.7 minus 0.4, and they all look like 0.3, but how many of these are actually distinct values? And this is just a mystery, right? Like there's no way for you to just look at this and recognize instantly like how many values there are. Okay, and so if I say how many values are unique out of these 5 things, 3 of them are unique. Okay, and I could ask, you know, if I say digits equals 20, we can see there's 0.29999, and there's 0.30004, and then there's 0.2999993. Okay, so there's okay, so this is very frustrating. Okay, and this is not the end of the lecture. Okay, and that, you know, that would be very depressing if I was just like, okay, your whole life is a lie, at least when it comes to computers. That's not the case. But now I've at least revealed this thing that says like, okay, when we're dealing with numbers on the computer, we have to be mindful of this happening. All right, and this is inherent to any time you have to represent a number that requires infinitely many digits to represent accurately, but you only have a finite number of digits, right? So for example, like if we didn't have a mathematical notation for dot, 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 or a bar to indicate like this thing kind of repeats forever, right? How could you represent the number 1/3 on a piece of paper, okay, using decimal notation? And it's impossible because you can't tell if somebody is actually trying to represent, let's say we're going to use 4 digits. Is someone trying to actually represent the number 1/3? Or are they just trying to represent, you know, 3,333 10,000ths, right? That actual fraction, 0.333000, or is it 0.333333333, right? And you can't tell if it's just represented this way, and so that's what we have. Okay, let's. A lot of you have seen binary representation before, but just in case you haven't, don't feel bad. We'll just do a quick recap of binary representation. So in binary representation, you only have 2 digits, 0 or 1, okay? And that's what we have to do, because inside the computer chip, basically our transistors, these microscopic transistors basically only have 2 states, on or off, okay? And now we're getting into kind of this quantum computing age where maybe we can represent more than just two states, but for for now it's two states. And so the first digit is your ones place, and so the next digit is your twos place, your next digit is your 2 to the 2, your fours place, and then the next digit would be your 2 to the third, eighths place, okay? So you have 2 to the third, 2 to the 2, 2 to the 1, 2 to the 0. So 0 would just be all zeros here, okay? So if I'm just using 4 bits here, I can represent 16 different values, starting at 0. Decimal value 1 would be all zeros and a 1 in the ones place, okay? 2 would be a 1 in the twos place and a 0 in the ones place. 3 would be 1 in the twos place, 1 in the ones place. 4, I would have 1 in the fours place, 0 out here, and 5, and so on and so forth, right? And so, this way you can count to 31 on one hand, right? You can go 1, 2, 3, 4, 5, 6, 7, 8. So you kind of, and you can count up to, so this would be 15, 16, 17, 18, 19, 20, 21, 22, 23, and so on. So, you can, so counting is actually reasonable, but then like trying to add like that is quite tricky. But anyway, so you can count up to 15 with four digits, okay? And then if you introduce the fifth one, you can get up to 31, okay? And so again, kind of looking at the number 1011, this represents 11. We have 2 to the third, you have a 1 in the eighths place, so you have an 8. We have a 0 in the fours place, so that would be a plus 0. A 1 in the twos place, so that's a plus 2, and a 1 in the ones place is a 1, and so this would be the representation of 11. Okay. Just like you have decimal values, okay, you can have binary values, and so once you have kind of this point, right, now over here it's called the decimal point, and over here it feels weird, but this dot is now called the binary point, okay? So you have values after the binary point, and values after the binary point, you have 2 to the negative 1, 2 to the negative 2, and 2 to the negative 3, and so on and so forth. So 1/2 in decimal is 0.5, but in binary it's represented as 0.1. You have 1 in the halves place. 1/4, 1/4 would be 0.25 in decimal, but this would be represented as 0.01, okay? You have 1 in the quarters place. 1/8 would be 0.001, and 3/8, okay? 3/8 would be 1/4 plus 1/8. 3/8, 0.375 is 3/8, and you have a 1 in the quarter place, a 1 in the eighth place, and this would be represented as 0.011 in binary. Okay, is this okay? Binary representation of, I guess, fractional values. So, like in decimal representation, most of your real numbers are going to have infinite binary representation. Okay, so for example, if you wanted to represent the decimal value 1/10, 0.1, okay, 1/10, this would have the binary representation of 0.0001100110011, so on and so forth, okay? Or, these 0011 would go on repeating forever, and it would require infinitely many values to return. But because the computer can only use a finite amount of bits, right? And technically we use 64 bits for all, like the entire real number line, and 52 of those are dedicated to the mantissa. This part's 52 bits long. It's going to be an approximation, right? It's just like cutting off the 0.333 at some value, okay? It's going to be a finite representation. And so when you try to do something like 0.1, it's represented this way. 0.2 also has an infinite binary representation, which is truncated at some point, okay? Or maybe rounded off at some point, and And so when we kind of combine these two together, we don't get the binary approximation of 0.3. So when you take the binary approximation of 0.1 and add it to the binary approximation of 0.2, it doesn't get that, okay? So let's delve into the standard that we are using for binary representation, floating point representation. Okay, before I go on, let me give you your second view quiz answer, which is the letter A. A as in apple. A as in apple. All right, so for pretty much almost all of our computer languages, we have floating point representation, and modern computers use the IEEE 754 standard for floating point representation. This is implemented at the hardware level on the actual computer chip itself, okay? So prior to this standard, different computer chip manufacturers would have different ways of storing numbers, and they said this is too crazy. So they came out with they created a specification, and it was kind of adopted by everyone, you know, in 1985. And this is done at a hardware level. So whether you're dealing with your phone, the chips on your phone, or your computer chips, your Intel chips, and now Mac has their own silicon, Apple silicon chips, and all of this. This is implemented at a hardware level, so it's gonna all of the numbers, whether you're using Python or R or C++, and pretty much because it's standardized across the entire industry, they're all gonna handle these numbers, you know, identically here. Okay, this standard was technically revised in 2008, but we'll take a look at the original specification, which is still fully contained in the 2008 revision. So the 2008 revision, I think, just kind of added to it. And you can read more on Wikipedia, just like every other topic. Okay? All right, so how do we do this? Okay? So if we were to have some normalized binary scientific notation, so if you think about scientific notation, where we say the digit before your decimal point has to be something other than a 0, so 1 through 9, okay? If you think about, okay, well, let's have kind of the equivalent in binary, right? In binary, we would say, okay, the value in front of your binary point has to be something other than 0. Okay, well then, because there's only 2 digits in binary, then it has to be a 1, okay? It's got to be a 1. And so here, we're going to have a few things. We need to have something that keeps track of our sign, whether it's positive or negative. And then we're going to have values for after the binary point, okay? Because we're going to always assume that the value in front of the binary point is a 1, okay? So after that, we're going to have some values stored here, and these will be 0s or 1, and then it will be multiplied by 2 to some power, okay? 2 to some power, all right? So this part, we've got the sign. This part over here we call the significand or the mantissa. You got mantissa bits, and then the last part will be the exponent, okay? And so when we store this number in the computer, we're going to store some of these things to be the sign, some to be the significand or mantissa, and some to be the exponent, okay? And then the leading one, right? So the number here, because it's always going to be led by a 1, there's no point in bothering to store it, right? Because it's kind of redundant at this point. Everything is it's a 1, so it's always going to be a 1. So you know, why bother storing that piece of information? So for example, we could take this decimal value 6.375 and represent it in terms of in binary floating point representation. So the 6 would have to be 110, 1 in the 4's place, 1 in the 2's place, and a 0 in the 1's place. So that's going to be the 6. And then the 0.375 is equal to 3/8. So you'd have 0 in the halves place, 1 in the quarters place, and 1 in the 8's place. And that would be 3/8. And so you would have 6 and 3/8, 6.375 here. Okay. And if we were to make this scientific, right, scientific notation, we would take this binary point, the point, and we would roll it forward over here, So I'm rolling it over 2 spaces. So this would become 1.10011, which is what I've got here. So 110.011 becomes 1.10011. And because I rolled it over 2 places, I'm going to say it's going to be multiplied by 2 to the second power. Okay? And so this also represents the exact same value of 6 3/8. Okay? And it's a little harder to read because now we're talking about, so I've got a 1 in the ones place, I got 1 in the halves place, nothing in the quarters, nothing in the eighths, 1 in the 16ths, and 1 in the 32nds place. Okay, so this is going to be 1 plus 0.5 plus 0.0625 plus 0.03125, 1.59375, and if we were to take this and multiply it by 4, we're going to get 6.375. Okay, 6.375. Yeah, question.
What are we doing to the power of 2? Is it because we are kind of like still so
So, okay, I'm not sure which part of the question you're asking about. So, are we multiplying by 2 to some power, or
yeah, like
versus 10 to the power, or is it 2 to the 2 versus 2 to the 3 or something?
Like why is it 1 point, like binary code times 2 to the power? Why is it 2 to the power?
Why is it 2 to the power 2? So in like, for decimal scientific notation, every time you move the decimal point over to the right or to the left, you're changing it by a factor of 10, right? You're either multiplying it by 10, and that would move the decimal over 1 space this way. Or if you divide by a factor of 10 or multiply by 10 to the negative 1, you're moving it over the other way, right? So if you had like the number 123, that would be 1.23 times 10 to the 2, right? You've basically moved the decimal point from 123, you move that point over 2 spots to 1.23 times 10 to the 2, okay? Here, we're in binary things, right? So this is 110, but these are binary values. So this 1 represents 2 to the 4, 2 to the 2, the 4's place. This 1 right here is 2 to the 1, the 2's place, and this is 2 to the 0, the 2's place. And I can move this binary point over a position, and to kind of get back to my original value, I have to multiply it by 2 to the 1. If I move this binary point over 2 spaces, and to get back to my original value, I have to multiply by 2 to the 2. Okay, because now we're in a base 2 system. So when I move the binary point, I'm multiplying either by a factor of 2 or dividing by a factor of 2.
Yeah, so essentially it's kind of like a conversion, because binary is like zeros and ones, but whatever 6.375, there's like 10 things to choose from. Is that what's kind of
I think that's what you're asking, and I think the answer is yes. Yeah, so yeah, this is the value represented. This is a binary representation using only 1s and 0s. This part, yeah, is 2 to the 2, and I'm using decimal notation here. If you insisted on a binary, it would be 2 to the 1 0. I think that would be confusing, but it could be 2 to the 1 0 instead of 2 to the 2. And then yeah, to kind of make it a little bit more visible down here, I'm using decimal notation down here. So the 0.1 becomes 0.5, and the 0.0001 becomes 1/16, 2 to the negative 4, 0.0625 in decimal. So that, yeah, you're not accustomed to working in binary, so it's okay that this it's kind of a slow thing, right? So as far as our computers go, right, there's technically different systems. You have single precision floating point, you have double precision floating point, there's also a long double precision floating point, okay? And so double, and that's why when you ask R, what is the type, it comes back type double. This is a double precision floating point, which means we use a total of 64 bits to store our values. We use 1 for the sign, 11 for the exponent, 52 bits for the mantissa, for a total of 64 bits in memory. So we're using 64 bits to store all of this, and this was a big deal back when I was a teenager, because you could buy the Nintendo 64 and 64 bits to store all of your stuff, and that was the thing. Okay, so if you think about how this is represented, okay, so you have these positions in memory, and it doesn't look literally like this, but you got these 64 bits. Okay, this bit is the sign. You've got 11 bits for the exponent, and you got 52 bits for the fraction or the mantissa or the significand. Okay, and this is how we're going to represent all of our numbers. And all of these things in here will be zeros and ones. Zeros and ones. Okay. So let's think about this exponent for a moment. Okay. The exponent, we have 11 bits in the exponent. Okay. So how many unique values can we represent in the exponent? With these 11 exponent bits, how many unique values can we represent? Okay, we can represent 2 to the 11. We can represent a total of 2,048 values. Okay, 2 to the 11 is 2,048. We reserve two of these values for special cases. Okay, the all zeros is a special case, all ones is a special case. All right, but everything else we can use to represent positive and negative values. So we have 2,046 values now. Okay. And we want to be able to represent both positive and negative values. Okay, so we divide 2,046 by 2, we get 1,023. And we're going to use 1,023 for positive values, 1,022 for negative values, and one of them for 0. Okay, so we're going to represent values negative from as low as negative 1,022 up to 1,023. Okay, so negative 1,022 will be all zeros but with a 1, and the 1,023 will be all ones but a 0. Okay, and we reserve the cases of all zeros for a special case and the case for all ones for a special case. And we'll talk about that later. Okay, so this, we say this has an exponent bias of 1,023. Okay, because technically if we were to convert this directly to decimal, this is a 1. But we're kind of remapping this. We want this to represent negative 1,022. So we're going to take the 1 and subtract 1,023 and get negative 1,022. And then this value, if you were to compute this all out, is 2,046. Okay, and we're going to subtract off 1,023 from this. If we converted this from binary to decimal, it's 2,046. We subtract off 1023. Okay, so we're going to subtract the value that we store in the exponent is actually adjusted by this exponent bias at 1,023. Okay, 2 to the 10 minus 1. All right, so if we were to kind of list off all the possible values that we can represent in binary notation, we have a special case for all zeros. The first value that we could possibly represent here in decimal is 1, but as far as the exponent goes, it gets stored as negative 1022. The next value would be all zeros 1 0. This is decimal 2 is internally stored as 1,021. Okay, and all of this becomes 1,023, and this is a special case. All right, the special cases of all ones is used when we have infinity or not a number. And then when we have all zeros, we go into what's called subnormalized mode or denormalized mode, and I'll talk about that later. So we're going to get into, we're going to run out of time, but let me give you how many view quiz answers have I given you? 2. Okay, your last view quiz answer for today is E. E as in elephant. E as an elephant is your last view quiz answer. E as an elephant. All right, so to kind of illustrate how this works, we're going to use kind of a miniature floating point system. This is a very rudimentary floating point system. We're going to have a total of 8 bits, okay? And we'll have 1 bit for the sign, 3 bits for the exponent, and 4 bits for the mantissa, okay? So this is like a miniature version of the double, okay? But the double has 1 for the sign, 11 for the exponents, and 52 for the mantissa, but we're using 1, 3, and 4. Okay? So for the sign, zeros, if it's 0, it's positive, and if it's 1, it's negative. Okay? And I think that's pretty straightforward. Okay? So technically there's 2 representations of 0. You have a positive 0 and a negative 0, but we won't worry about that. Okay? All right, so let's talk about the exponent. So here we're going to use 3 bits for the exponent, which means we can represent 8 unique values. 8 unique values. And we're going to have a special case for 0 and a special case for all 1s. Okay? So if I list them all off, in binary I go 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 1, 1, 1, 1, 0, 1, 1, 1. Okay? And this becomes 0 through 7 in decimal. And so if we think about, okay, if I can represent 8 unique values, and I want half of them, or we take away 2 of them for special cases, I'm left with 6, okay? And then I want half of those 6 to be positive and half to be negative. So, you know, technically we need to have 1 for 0. So we're gonna have a bias of 3. So 6 will become 3, 5 will become 2, 4 will become 1, 3 will become 0, 2 becomes negative 1, and 1 becomes negative 2, okay? So we're gonna be able to represent basically just 1 more positive value than 1 negative value. And this is kind of an arbitrary choice, but they said, yeah, let's go with 1 more positive than the negative side, okay? So half of the remaining 6 will be positive, then you have 1 for 0, and then the rest will be negative, okay? So this means we have a bias of 3, okay? Because the 6 becomes 3, the 1 becomes a negative 2. We're basically subtracting off 3 to go from the decimal to our biased value, okay? And so our exponent bias is 3. In general, if you have n bits for the exponent, the amount of bias is going to be 2 to the n minus 1 minus 1. Okay, so our exponent bias is 3. And then the remaining 4 bits will be used for the mantissa. All right, and so we're always going to assume in binary exponential form, you're going to have 1 point something, 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 and these 4 bits, these somethings, are represented by the mantissa. So okay, I'm out of time, but basically, if we break this down, we've got 0 for the sign, so it's going to be a positive number, 1, 0, 1 for the exponent, and 0, 1, 1, 1 for the mantissa, okay? The exponent bits are 1, 0, 1. The mantissa bits are 0, 1, 1, 1, okay? So as far as the exponent bits are 1, 0, 1. If I go back to kind of my table, 1, 0, 1 and decimal is 5, I've got a bias of 3, so this becomes 2. Okay, so this is 5, the bias is 3, the exponent value is 2. Okay, the mantissa bits are 0, 1, 1, 1, so this becomes 1.0111 and 1.0111, and then we got 2 to the 2. So if I do this, we're going to have 1 plus 0 halves, 1/4, 1/8, 1/16, multiplied by 2 to the 2. So if I do this, we're going to have 4 plus 0 plus 1 plus 1/2 plus 1/4, and I get 5.75. Okay, let's end here, and we'll see you on Wednesday. Wednesday's the midterm. Okay, so you'll get instructions from me regarding the midterm exam, but I'll see you guys on Wednesday, either here or in the evening in Kinsey 1240B. Okay, good luck as you study, and we'll see you guys on Wednesday.